Welcome to the video for lesson 3.3, constructing perpendiculars to a line. I know the anticipation waiting on this video must be killing you. I imagine it's similar to how hard it is for you to wait for a Taylor Swift album to come out because you just love her music so much. If you see on the bottom, it's another creative thinking. This is not a visual thinking. This is more of a creative thinking, which is why I wrote creative thinking. And it tells you to move 6 matches to make 10. It is a kind of a little trick to it. So I hope you do well with that. If you want to pause it and try to get that, the people that get it will get even better than the last time, which will be this time they get a piece of candy. How exciting. So what we're doing today, like I said, is learning how to construct perpendiculars from a point to a line. The difference here is we've learned how to construct perpendicular bisectors. But what if you're trying to draw a perpendicular from this point P to that line AB? You need to be able to know how to draw that perpendicular if the point is not in the middle. So what we first do, like almost always, is we draw a line, okay? And we're going to have a point like they have, point P. And we're trying to draw a perpendicular from this point to that line. So we line up our compass. We want to make sure that our arc that we're going to make intersects this line twice. Okay? So that actually works, but I don't like it because I want you to make sure you can see it. So let's do this again. Let's make point P. When you make this, you want your compass to be a little bit farther than that line, and you can see you make it a little bit farther right there, but you also want it to be able to intersect that line. So there we go, this intersects it twice, both sides. You see that? Then if you line up your compass with the 2 intersection points, you can now move the compass however you want, as long as these 2 new arcs intersect. And you line up your compass with the other intersection point. And as long as those intersect, you are golden, because now what you've done is you've made your perpendicular. That line is perpendicular, 90 degrees. You can measure that if you've made this yourself. You can measure that on your paper with a protractor. That's how you make perpendiculars. So now I want to talk about what we know about perpendiculars. We just constructed one. But let me use a real life example. Hopefully this doesn't apply to any of you. I really hope this doesn't apply to any of you because we're talking about robbing a bank. But let's say you are robbing a bank and a cop shows up really quickly. You were a little surprised how quickly. So when you walk out of the vault, you're not expecting it, but you see a police officer talking to the bank teller, trying to figure out what's going on. The officer knew something was wrong because to get in, this was a high security bank, you had to blow up an entire side of the wall. So one side of the building is completely open. You see the officer sees you. You have a little quick stare down. You want to get to the wall as quickly as possible. The only way to survive is to get to there as quickly as possible, because the officer, knowing he can't run you down, is going to pull out his gun and see if he can slow you down. Maybe shooting you in the leg or something. So you want to get to that wall as quickly as possible, and the way to do that is to know the exact line to run in to get outside in the shortest distance, because that's where your getaway car is driving. And most likely it's Cameron driving the getaway car, because she's kind of a suspicious character anyway. So to do that, we're going to switch the side to find the shortest distance, not the slowest. You do not want to be slow in this case. You want the shortest distance. I'm always going to draw this line to represent the wall, and then we're going to draw a point to represent you, whoever you are. And then over here is the getaway car. Cam's waiting, screaming for you to hurry up. I don't know why Cameron does not have a faster car than this one. It's kind of slow. Anyway, you're trying to find the shortest distance. Well, how do you find the shortest distance? Well, the shortest distance is going to be the perpendicular line. So if you look, you draw that line down, Do you think that would be the shortest distance? Do you think that would be the shortest distance? That would be the shortest distance? All these points I can draw. These are lines you can run to get to the wall. And the question is, what's the shortest distance? Well, it's the straight one that's perpendicular to the wall. That's the shortest distance. So when we measure distance, what do? We measure them from the perpendicular segment. So I want you to write this down as the first part of your notes, besides for the drawing. The shortest distance conjecture. The shortest distance from a point to a line is measured along the perpendicular segment from the point to the line. This is not a perpendicular bisector. I'm going to tell you that again because I don't want you to get confused. This is how we draw a perpendicular from any line or any point, not just the middle points. And you can see up here on the right, similar to what I just did, it shows you the shortest distance is PM, which is the perpendicular segment. So I also want you to write down these two definitions, which is the distance from a point to a line. That's the length of the perpendicular segment from the point to the line, which is similar to what I just said. The distance you measure, if say, what's the distance from this point to that line? It's only the line that is the perpendicular segment. And then the altitude of a triangle, a new definition, altitude, a perpendicular segment from a vertex to the opposite side, or a line containing the opposite side. Now it's important to add that second part, and you can see from this middle picture why it's important to add that second part. If we're drawing the altitude from this red little point here to this baseline, and I'll highlight this, down here, a perpendicular segment doesn't exist inside of the triangle. So you have to draw this dotted line right here to kind of extend this triangle out to draw your altitude. That, if you notice, is an obtuse triangle. So all obtuse triangles, altitudes will be outside of the triangle. On the far left here, if we have our point and we draw the altitude down to this line here, the perpendicular is going to be inside the triangle because it's an acute triangle. All acute triangles will have altitudes inside the triangle. And then over here we have a right triangle. Now I know that these have 90-degree angles on the left and the middle one, but those are 90-degree angles formed for the altitude. Those are drawn in after we make the altitude. Here, this is a right angle that already has a 90-degree angle, and the altitudes, because what you're trying to do is draw from point to the base, or this point to that base, the altitudes are just the legs of the triangle, the two sides, the non-hypotenuses. Hypoteni, I don't know which one it is. Hypoteni sounds nice. And so I want you to see, left is acute, middle is obtuse, right is right triangle. Doesn't that fit well? Right is right triangle. Just sounds so perfect. So anyone in this class that plays baseball and knows about baseball will kind of see what I'm talking about here. If we're making an angle, and our angle is the first baseline, which I'm covering in red, in a perfectly straight line, and the third baseline in a slightly more perfectly straight line, if that's my angle, and this is my vertex, home plate, we have a perpendicular, or an angle bisector, because this is what we're doing. We're constructing angle bisectors, which you should title this new part. We have an angle bisector, this dotted line that goes through the pitcher's mound and through second base. If that's the angle bisector, then from the pitcher's mound, drawing a perpendicular line to the third baseline, and drawing a perpendicular line to the first baseline, those will be the exact same distance. They will be congruent. The same with second base. If this is the angle bisector, the little dotted black line, from second base to first base, and from second base to third base, you draw the perpendiculars, and they are the exact same distance. Okay? That's how they make the baseball field. But now that we know that, I want us to show it by being able to draw an angle bisector. So, to draw an angle bisector, we first need to have an angle. To make lemonade, you first have to have lemons. To make hash browns, you first have to have potatoes. So let me, very similar to that, make the angle. And after you make your angle, you're going to draw an arc, and the arc can be any size you want. Let me see if I can make that blue. Any size you want. Then you go to, in this case I would say going big or going home, I'd rather go home because going big here might actually make it more difficult, but you could. Now you make from the intersection point of the arc you made with one side of the angle, you put your compass and you draw another arc, and then you go to the other intersection of the arc and the other side of the angle, and you do the same thing. You make another arc, and look, our arcs intersect. Who would have thought? Start at the vertex, go through that intersection point, and that is our angle bisector. These two angles are congruent. If that's angle 1 and that's angle 2, you can write angle 1 is congruent to angle 2. Unbelievable. Come on, compass, get out of my way. Wow, that looks terrible. Angle 1 is congruent to angle 2. There we go. That looks only slightly better. Anyway, you get the idea. So that's how we bisect an angle, and we know those two are congruent, and we also know that any point we pick on this angle bisector, if we draw the perpendicular to the other side, or to the side of the angles, if we draw the perpendiculars, those are congruent, just like we talked about with the baseball field. Any point, this is true, you're drawing the perpendicular to the side of the angle. All these, any points you can draw, they're going to be congruent. The distances will be congruent. So the last slide is the last thing we're doing. What I want you to be able to do is I'm going to show you how to do the 45-degree angle. I'm going to show you how to create a 60-degree angle, and then I want you, the harder version, create a 75-degree angle. This is a very creative thinking and problem-solving problem. To create a 45-degree angle, we first want to create a 90-degree angle, because then we're going to bisect it. Well, how do we create a 90-degree angle? We draw a perpendicular bisector. So we take our compass. Remember, we have to go over halfway. That's key. If we don't go over halfway, then the lines that we make, the arcs we make, will never intersect. That looks over halfway. And then we draw an arc. We come back to that, to the other side of the line. And if I'm exact, we draw another arc. And what do we have now? We have a perpendicular bisector. If we just connect those two, that is our perpendicular bisector. So that means we've made 4 90-degree angles. We can take any one of those angles and then use what we just learned to create an angle bisector. And to bisect a 90-degree angle is going to give us 45. That's what cutting a 90-degree angle in half will give us a 45-degree angle. So what do? Then we make an arc any size. We can change this size if we want now. And we make 2 new arcs. Boom. There we go. Now we connect those. There's our angle bisector. And now I'm going to erase all this stuff that I just drew in there. Just know you wouldn't need to do this. Now we know we have a 45-degree angle. And either one of these will be 45. You could use the top or the bottom. Now we want a 60-degree angle. And how do we do that? Well, the way I would do it is, I know an equilateral triangle has all 60-degree angles. So remember, if we learned how to do an equilateral triangle. If you didn't, on the mirror day, you draw your line, you use your compass to measure that line, and now we know the measurement of that line. And then to get the exact spot that they will intersect, what do? I draw 2 arcs, one from my compass being on one side of this line segment, the other from my compass being on the other side of this line segment. And where they intersect is going to be the intersection point of our equilateral triangle. Because if we don't move our compass, what you can see is that distance, and then we come to this side, and that will be that distance. And that's how we know that intersection point is our equilateral triangle. There we go. Equilateral triangle. Here's a 60-degree angle. They're all 60, so any of these could be your 60. Now what I want you to do is make a 75-degree angle. And again, this is problem solving. This is, maybe you don't get how to do it right away and you think, how can I add up to 75? What do I know to add up to 75? I know you enjoyed this video, because how could you not? And I hope you enjoy your weekend.